Okay, so welcome back to this next video in which we are discussing the P2Y receptors. Okay, right, so we're in the process of discussing the heterotrimeric G proteins and the G protein cycle. Okay, so we want to discuss all the different genes that you have for alpha subunits, so the 16 different genes for alpha subunits. Okay, right, so let's get a new piece of paper and do this. So, to help us make sense of the different genes for alpha subunits, they are grouped into 4 major families, and these groupings are to do with their activity. Okay, so we group alpha subunits together based on what they then do, basically. Okay, so let's start off with the first family of alpha subunits of heterotrimeric G proteins. So the first family is called the G-alpha S family. Okay, so this is common notation. You put a capital G for to illustrate that we're talking about a heterotrimeric G protein. Then you put alpha, because we're talking about alpha subunits, and you subscript it then with which specific alpha subunit we are talking about. Okay, now we're talking about the G-alpha S family at the moment, and this family contains the G-alpha S subunit itself. Okay, or rather the G-alpha S gene, because this has multiple splice variants. Now, as far as we know, all of the splice variants do pretty much the same thing, so we'll just talk about the gene, which is the G-alpha S gene. Okay, right. The next alpha subunit of a heterotrimeric G protein that is also in this G-alpha S family of alpha subunits of heterotrimeric G proteins is G-alpha OLF. Okay, now the G-alpha OLF gene and its corresponding protein subunit seems to do pretty much exactly the same thing to G-alpha S. Okay, so it activates adenylyl cyclase enzymes. Now, in the olfactory epithelium, you have a lot of G-alpha OLF and very little G-alpha S. So it appears that in certain portions of the body, G-alpha OLF replaces G-alpha S, but it seems to do pretty much exactly the same thing. So it makes sense to group these two together. Okay, and because of its presence within the olfactory epithelium, that's where it got its name, G-alpha OLF, OLF for olfactory. Okay, right. So the next family of alpha subunits of heterotrimeric G proteins is the G-alpha I/0 family of alpha subunits of heterotrimeric G proteins. Okay, and this family is the biggest of all of the families of alpha subunits of heterotrimeric G proteins. This is going to contain 8 different genes. So, let's start off with the G-alpha I genes. Now, it might surprise you if you're seeing this for the first time, but there are multiple G-alpha I genes. There is G-alpha I1, there is G-alpha I2, and then there is also G-alpha I3. Now, all of them seem to do pretty much the same thing, okay? But they are separate genes, and they do code for separate proteins which will have different sequences of amino acids. But as I say, all of them seem to do pretty much the same thing, which is that they inhibit adenylyl cyclases. Okay, so they're 3 of the members of this great family. Then you also have G-alpha O, which again does very similar things to the 3 G-alpha I's. Okay, then we have the G-alpha T's. Okay, so there is G-alpha T1 and G-alpha T2. Now let's discuss these two. So basically, in the rod and cone cells within the eye, there are G protein coupled receptors which are sensitive to light. Now in the rod cells, this G protein coupled receptor is rhodopsin. Okay, now the G protein coupled receptors in rod and cone cells, when light hits them, they're going to be activated to interact with a heterotrimeric G protein, and the heterotrimeric G proteins which they interact with are known as transducins. Okay, now the transducin within rod cells is different from the transducin in cone cells. Okay, so you have rod transducin and then also cone transducin. And in rod cell transducin, the alpha subunit is this G-alpha T1. Okay, so this is the alpha subunit within rod transducin, and in cone cells, the G alpha T2 is the alpha subunit. Okay, so this is the alpha subunit within cone transducin. Okay, now these have very different functions from these. Okay, these inhibit adenylyl cyclase enzymes, okay, and therefore reduce the production of cyclic AMP. Whereas the alpha subunits of transducin heterotrimeric G proteins, these will go off and activate phosphodiesterases, specifically phosphodiesterase 6, and then they lead to an increase in the activity of phosphodiesterase 6, and it breaks down cyclic GMP. Okay, so they also lead to the reduction in the level of a cyclic nucleotide, but it's cyclic GMP, and the mechanism is different. Rather than stopping it being manufactured, they increase the rate at which it's destroyed. Okay, but because their function is kind of related, they're also affecting cyclic nucleotide levels, and they're reducing them. And they are grouped together with the I's and the O's, the O, in this family of G-alpha I/O. Now, whilst we're on the subject of O's, I should just mention that G-alpha O has 2 splice variants, and I said I wasn't going to mention the splice variants, but the terminology for the splice variants of G-alpha O is quite, it's set, okay, so I'll give you it, okay, and you'll come across it if you read papers. So there is G-alpha OA, and there is also G-alpha OB. These are the 2 different splice variants of the G-alpha O gene, okay, so they're not separate genes, they're different alpha subunits which come from the same gene. Okay, right. Now we haven't finished with this family. There are 2 other members, and these are the ones that almost no one has ever heard of. So there is GZ, whoops, I've missed off the alpha, it's G-alpha Z, okay, and then there is also G-alpha GUST, which is involved in transduction within the gustatory system. Okay, right, so those are the 8 alpha subunits of heterotrimeric G proteins which are clustered into this family of G-alpha I/0. Okay, the next family then. The third family is the G-alpha Q/11 family. Okay, and this contains the famous alpha subunit G-alpha Q. It also contains G-alpha 11, so that it contains the 2 after which the whole family is named. And then it also has 2 other members, okay, which are G-alpha 14 and then also G-alpha 15/16. Now this is only 1 alpha subunit. Do not be confused into thinking that this might be 2. So just to make sure that you never get confused with this, I'll give you the story as to how it came to be called G-alpha 15/16. So basically, there were 2 groups of researchers. One was working in mice, and they found a new alpha subunit of heterotrimeric G proteins, and they called it G-alpha 15. Okay, so this was found in mice. Okay, then another group of researchers then were working in humans, and they found a new alpha subunit of heterotrimeric G proteins, and they called it G-alpha 16. Okay, later it transpired that actually this G-alpha 15 in mice was actually just the mouse equivalent of G-alpha 16 in humans, or if you like, the G-alpha 16 subunit was just the human equivalent of G-alpha 15 in mice. Okay, so there was then a concerted effort to have both of them renamed G-alpha 15/16 because we don't want it to be called something different in mice and humans. That's just confusing. Now we're even worse off because some people use G-alpha 15/16. Some people who are loyal to mice will continue to use G-alpha 15 with regards to mice genetics, and some people will use G-alpha 16 with regards to human. Okay, so be aware of that, basically. It would be nice if you called it G-alpha 15/16 to show willing. Okay, right. Now, all 4 of these alpha subunits then, these are all involved in the activation of phospholipase C beta family enzymes, okay, and they therefore lead to the breakdown of phosphatidylinositol 4,5-bisphosphate into inositol 1,4,5 trisphosphate and diacylglycerol, and then the IP3 leads to the release of calcium from the intracellular store, and together the diacylglycerol and the calcium activate protein kinase C enzymes. So they're all involved in that pathway, all of them. People know generally that G-alpha Q is involved in that, but actually all of these three also do that. So they have very similar functions to G-alpha Q. Okay, right, so they're all grouped together into this family here. Now the final family is the one that no one has ever even heard of a single member within it. Okay, so generally people have heard of G-alpha S, G-alpha I, and G-alpha Q, so they've heard of at least one member from these three families. The final family is the G-alpha 12/13, and this is more niche knowledge. Okay, so this contains two members. It contains G-alpha 12 and G-alpha 13. And these two are involved in cytoskeletal remodeling. Okay, so let's make sure that I have actually given you 16 different alpha subunits then. So let's count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11, 12, 13, 14, 15, 16. So there are the 16 different genes for alpha subunits of heterotrimeric G proteins. Okay, right. So now let's go over to the beta subunits. We've talked about all the different alpha subunits. Let's now talk about all the different beta subunits and all the different gamma subunits. Now don't worry, the G beta subunits will not take us as long as the G alpha subunits, okay? So we'll be done soon, and then we can get on to the more interesting stuff. Okay, right. So G beta subunits then. There are 5 genes for G beta subunits, okay? And these code, for a total of 6 different subunits, okay? And we're now perfectly equipped to understand this, okay? We therefore know that one of these genes must have 2 splice variants, which would then explain how 5 genes can give 6 different subunits. Okay, and that is indeed what has happened. So, the 5 different genes then, what are these called? Well, they're given a beautiful naming system, okay? So we have G beta 1, G beta 2, G beta 3, G beta 4, and then finally G beta 5. So perfect, easy to remember. There's nothing to remember really. Okay, right, so these are the 5 genes. Now, which one has the 2 splice variants? Well, it's the G beta 5 that has 2 splice variants. And the 2 different proteins that it can give rise to are called the G beta 5, so named after the gene, and then there's the 5 splice variant, and then the second splice variant is called G beta 5 and then L. So those are the names of the 2 different splice variants that come from the same gene. The other 4 genes only give 1 splice variant at least, which is known, and therefore the G beta 1's protein is called G beta 1, the G beta 2 gene's protein is called G beta 2, and so on. Okay, so it's only with G beta 5 that you need to be careful about the naming of the 2 separate proteins that it can give rise to. Okay, so that's G beta subunits, and now finally onto G gamma subunits. Okay, so the gamma subunits of the heterotrimeric G proteins. Here there are 12 different known genes. Okay, so there are 12 genes known, and there are only 12 subunits. Okay, so no splice variant nightmare here. Okay, so the naming is almost perfect. It has one little blip in the nice naming. Okay, so basically the naming of the gamma subunits goes G gamma 1, G gamma 2, G gamma 3, G gamma 4, all the way up to G gamma 5. And then there is no G gamma 6, which is just annoying. And then it goes on to G gamma 7, and then you continue on, and you have to go past 12 now. You have to go all the way up to G gamma 13, because we missed one out. Okay, so there's G gamma 7, G gamma 8, G gamma 9, G gamma 10, G gamma 11, G gamma 12, and G gamma 13. Okay, and those are the 12 different genes, and therefore also the 12 different subunits that we can have as gamma subunits. Okay, so now we're aware of the total incomprehensible scope for different heterotrimeric G proteins. You have in total, if you're building a heterotrimeric G protein, 21 different alpha subunits to choose from, 6 different beta subunits to choose from, and 12 different gamma subunits to choose from. Okay, and that's only the ones that are known at the moment, and these numbers will almost certainly change in the future. Okay, right, so what I want to now discuss is the naming of heterotrimeric G proteins. Okay, so ideally, when we're naming a heterotrimeric G protein, people would tell you exactly which alpha subunit you are dealing with, exactly which beta subunit you're dealing with, and exactly which gamma subunit you're dealing with. So let me give you an example of the perfect world. Okay, so in the perfect world, this would be the naming of heterotrimeric G proteins. You tell me exactly which alpha subunit you've got here. This is the G alpha I1 subunit. Then you tell me which beta subunit you've got. You've got the beta 1 subunit. And then you tell me which gamma subunit you've got, the gamma 1. People very rarely know this sort of information. Almost never do they know what the beta and the gamma subunit are. Okay, so instead, usually what happens is when we name heterotrimeric G proteins, they're named after which alpha subunit they have, and that's just because people don't know which beta and gamma subunit they have. Okay, so we'd call this G, and then we'd subscript it I1, and this would tell us which alpha subunit you have. Now, often people don't even know which alpha subunit they specifically have. For instance, I told you that G alpha I1, G alpha I2, and G alpha I3, they have almost indistinguishable properties. Okay, so they often don't know which specific alpha subunit you're working with. Okay, so people might call this GI instead. So when people say that the G protein coupled receptor activates GI heterotrimeric G proteins, what they mean is that they are activating heterotrimeric G proteins where the alpha subunit is one of the I's, okay? So it could be G alpha I1, it could be G alpha I2, or it could be G alpha I3, because they don't know which of the exactly which one it is, and potentially, the G protein coupled receptor is activating all 3 of them. Okay, so it's pointless distinguishing between the 3 anyway. Okay, right. Now, sometimes people don't even know that sort of information, okay? So sometimes they only know that it's within the family, okay? So for instance, someone might call this a G alpha I/0, saying that the alpha subunit is within the family of G alpha I/0, okay? And usually when people say this, they'll be meaning it's either one of the GIs or it's a GO, basically. They generally will be able to distinguish between those and, for instance, the T's, okay? So it generally, if they put GI/0, they won't mean one of the transducins. They'll put GT if they mean that, okay? Because those are distinguishable from these 4, okay? Similarly, if people are dealing with a heterotrimeric G protein which has one of these 4 subunits in, they'll put GQ/11, okay, which means that the alpha subunit is within this family. And I told you that all 4 of these pretty much do the same thing, so often it's very difficult to tell whether your G protein coupled receptor is specifically activating G alpha Q or whether it's activating some of these related ones, okay, and that's why people will put GQ/11 to mean one of these 4, basically, okay, and then it activates the same pathway, okay, so it doesn't matter which of those alpha subunits it is. Okay, so that's the normal naming system for heterotrimeric G proteins, that you subscript it with details regarding which alpha subunit it is, and often people don't tell you exactly which alpha subunit it is. They give you a general idea, so GQ/11 means that it's one of those 4 within the G alpha Q/11 family. GI/0 means that it's within the G alpha I/0 family. although you can exclude the T's from that. Okay, so you wouldn't look at this and infer, oh, it's a transducin one that's working. Okay, people would put GT if they meant one of the transducin ones. Okay, and generally people do know whether they're dealing with GT1 or GT2. Okay, right, so that's just a little bit on the naming system for heterotrimeric G proteins. Okay, right, so in the next video what we'll now turn our attention to is the G protein cycle, okay, which is how G protein coupled receptors activate the heterotrimeric G proteins, and then how the heterotrimeric G proteins are going to interact with downstream targets.